to 0, for example. So at any rate, these numbers are not wildly far apart. So somewhere in the range of 50 to 60% of the selenium seems to be tying up in the sediments. And that's the total depth of sediments. And again, very preliminary numbers. We also looked at the selenium concentrations in the macroinvertebrates. And by the way, all of our analysis were done by Reich in Beckley, one of our better labs, and all of, most of that's, all the aqueous selenium was done by hydride generation, which I think is the best method to use. But anyways, so macroinvertebrates, Mud River, Reservoir, and then Plum Orchard Lake. Averages, and we sorted them out by functional groups, or Reich did. And we wound up with about, in the Mud River, about 8.8 milligrams per kilogram, in the reservoir, 7.5, and then our reference site, Plum Orchard, 1.6. So substantial biomagnification in the macroinvertebrates. Preliminary conclusions. So there's significant biomagnification in the macroinvertebrates and the fish tissue. No question about that. Surprisingly high gonadal selenium concentration in our reference reservoir, and we'll check again now on that this summer. But we haven't really seen any significant impacts on the fishery. There are apparently a lot of breeding going on. We haven't seen a lot of examples of strange-looking fish. And I did look at the Campbell report, the WVDEP report with the shortened upper jaws, and we've seen pictures of those. I'm not sure what that is. I've been told by some people that that's a hatchery deformity. Whether it's that or selenium, I don't know, but there's an awful lot of selenium in the fish themselves. So, to put things in perspective, I tried to translate a lot of these numbers into human toxicity because we'll let the fish toxicity work itself out. Just to give you some idea of where you start to get concerned, these are numbers. I got this from the Oregon State website. They deal with selenium as well as other stuff. Selenosis occurs at a daily intake over 5,000 micrograms per day. The maximum daily dosage is, comes from the NAS, I believe, 800. Upper daily limit is about 400 micrograms. And you get selenium deficiency at about 11 micrograms per day. Cancer risk reduction, according to the theorists, we think that the antioxidant properties are very significant with selenium. They like to see 200 to 300. And 300 plus 100, which is about what a healthy diet ought to give you every day, gives you this 400 number here, this UL limit. So that's all worked into that calculation. And then you start getting adverse selenium effects in humans between 600 and 1600 micrograms per day. So in terms of Mud River water, what does that translate into? And if you were to look at how much it would take to give you selenosis, you'd have to drink 88 gallons per day, every day of the year. So obviously that's unlikely to happen. So this then trails off. But what about the fish? And these are the daily dosage requirements of fish to give you selenosis versus your average, your required amount every day. And these are odd numbers, so I translate that into how many you'd have to eat over the course of a year to give you selenosis, and it would be a whole lot, 200 some pounds of it. And to get you your upper daily limit, 16 pounds over the course of a year. And somewhere between 30 pounds per year and 200, you might start getting into human health effects with selenium. So just to give you some rough idea. And of course that's based on whole fish, basomatic selenium, not just taking out the flesh, which may be higher or lower, I don't know. Maybe someone out there knows whether that should be higher or lower. Okay, so then we get into at-source selenium control. So letting selenium get into the river is obviously a bad thing. What do you do to keep it on the mine site so it doesn't get into the ecosystem? So we did a bunch of humidity cells, looked at a number of different treatment options at the mine itself. And the fundamental chemistry is this. Selenide, which starts out as, you think it starts out as an iron selenide mixed in with pyrite. That's probably where most of the selenium comes from. Everyone I've talked to agrees that that's probably where all the active selenium is. Oxidizes to selenite initially, which will stick to ferrohydrite, among other stuff. And then if that in turn slowly, it's not a quick oxidation, but it slowly oxidizes up to selenate, which is highly mobile. Once that gets into the environment, the cat's out of the bag. So you're trying to catch it at step number 2, at selenite. So we did some coal leaching studies with pit cleanings from southern West Virginia, and we found out that there's a relatively regular selenium leaching rate, and we're finding that we've not only identified how much of the selenium in total, the total selenium is actually mobile in the environment under ambient conditions, we have a reasonable idea of what that rate of release looks like. So this is a paper that was recently published by Ron Smart and some of his graduate students from the chemistry department here. And he looked at a new method for determining how much of the selenium is mobile and compared that against sequential extraction, which is how we've done some of our earlier work, like with Dorothy Vesper a couple years ago. And what it looks like is he's coming up with almost identical numbers that Dorothy came up with, which is about 25% to 33% of the total selenium in the coal-associated rocks is mobile, and the rest of it's just residual. You just can't get it out of the rock. This was published in Chemosphere just this month, by the way. So here's the result of our leaching study. This is over 52 weeks, right over here in the lab. The red squares are controls, and when you bring selenium-bearing rock into the lab, your first leach has a lot of selenium coming out of it because it's been sitting there oxidizing primarily away. And selenium oxidation is a lot faster than pyrite oxidation, for example. We found that out. And here's the control here, and they're getting well over up in the 15 to 20 microgram range. And we corrected this leachate liquid to solid ratio by looking at chloride. We actually had chloride we measured coming out of our leaching apparatus, and we knew the chloride coming out of the field pile, for example. So that was a several million ton pile of rock. So we used that to correct the concentrations to what you might actually get in the field. And when we did that, the selenium concentrations matched up almost perfectly to what was coming out of the several million ton pile down the southern part of the state. So, to make a long story short, when we added ferrohydrite, we tried other stuff, but it didn't work very well. The concentration stayed below 5 micrograms per liter by and large. And this is the oxidation rate. This blue line is projecting out to 66 weeks. And that's what it should be if your rate is about 0.07% per day, and 33% of the selenium is mobile. The orange diamonds are the actual observations. So you can see we diverted from our prediction about week 36, and it starts going into a slower decay curve. Same thing. So we're down now to about 0.05% per day, which doesn't sound very much, but it is a lot. This is projecting over a 10-year period, 500 weeks, what how long it would take for all the selenium in that rock to go away into the environment. And about 90% of it's gone after 500 weeks at that rate. Now, it seems to be slowing down, which could either mean one of two things. One, there's even less mobile selenium than we thought originally, or it's going to go into a different curve and then just start creeping up here more gradually. I'm not really sure yet. So compared to sulfide oxidation rates, and this is all good geochemistry here, these are the kind of rates you might get in coal, iron, sulfides, about 0.006% per day. That's about 1/10 of what we're getting here with selenium. Hydrothermal pyrite's even slower by an order of magnitude. So somewhere between 10 and 100 times faster, depending on what benchmark you're using for pyrite oxidation